All right, how's it going? So we're going to continue in our series of irrotational flow lectures by talking about the Laplace equations today. So the objectives of this lecture are to derive and characterize the Laplace equations, and then to show how we can obtain the pressure using the solution from the Laplace equation. So the Laplace equation gives us the velocity field. And then if we take that velocity and insert it into the Bernoulli equation, we can get the pressure field. And then I'm going to introduce the unsteady Bernoulli equation. And then we'll talk about boundary conditions, what's necessary to solve the Laplace equations. And then finally, I'm going to run through a quick solution of the Laplace equations to show you how it all fits together. All right, so let's start with the Cauchy-Riemann equations that we've discussed. Here they are. It's a relationship between the potential and stream functions in 2D space and xy coordinates, so Cartesian coordinates. And if we cross-differentiate the first one, so we're going to cross-differentiate this equation with respect to x, you can see that we get this, right? Partial psi squared, partial x, partial y, plus partial phi squared, partial x squared. And then we do the same. We're going to cross-differentiate the second Cauchy-Riemann equation with respect to y, and we get something very similar. Notice that this term and this term are the same, and so we can equate those two terms to end up with this second-order equation that describes phi. So it's the second derivative of phi with respect to x and the second derivative of phi with respect to y. All right, so it's a second-order equation in space, and this is the Laplace equation. I can write it more compactly using the del operator. Del squared phi is equal to 0. So let's characterize this equation. You know, I often like to think about old movies. You know, when you see these old movies, a lot of times there's a scene in the end where there's a villain and there's a good guy, and at some point the villain's mask gets taken off, like in Star Wars, right? In Star Wars, Darth Vader's mask gets taken off. Or better, these B-grade Chinese fight films where the hero roundhouse kicks the bad guy and his mask goes flying off and everybody is shocked, right? They're like, oh, they see the bad guy. Well, in some cultures, the idea is that you can't defeat an enemy without seeing their true face. And so, I think it's the same with differential equations. We can't solve these differential equations without revealing their true nature. And so, to go through this part where we characterize the equation is an essential part to roundhouse kicking these equations and defeating them. All right, so enough of that. This Laplace equation, it's second order in space and in time. And so that essentially means that we're going to need two boundary conditions, right? We're going to need one in x, or two in x and two in y. It's a linear equation, right? Although this is del squared, this squared operates on del, not on phi. So it's linear in phi. And so that means that a solution does exist. We know for a fact that linear equations have solutions. It also means that we can add these solutions together to create new solutions. And this is called superposition, right? So if we have one solution, it's the solution to the Laplace equation, we have another one, we can add these two together to get a third solution. That is superposition. It's a homogeneous equation, meaning that every term that's non-zero contains the dependent variable. And so what does that mean, that it's homogeneous? It means that it could be an eigenvalue problem, which leads us down a whole different path to defeating this equation. So keep that in mind moving forward. It's especially true because of the whole reason that we are interested in orthogonal functions is that it is another mathematical tool we use to solve eigenvalue problems. Thirdly is that this equation, as written here, is three-dimensional. So it's interesting that the potential function is three-dimensional, but the stream function is two-dimensional. Here they all are. So I've written out the equations in Cartesian, spherical, and cylindrical coordinates so that you can see them all together. And these equations were named after Pierre-Simon Laplace. So Laplace was born, I should say, not long after Newton died, and he had a huge influence on physics in the day, mathematics, and so he is known as the French Newton. That's quite a title. All right, so in addition to solving this equation being valid for irrotational flow, it also pops up in electromagnetism and astronomy, and you've seen it in heat transfer. Del squared T is the diffusion equation. So it is quite useful in solving all kinds of problems. Take that. All right. You could show that using the Cauchy-Riemann equations that if this is an equation that governs phi, the potential function, then it can also be cast in terms of psi, the stream function. And I'll leave it to you to prove this kind of as a try your hand coffee break maybe. This is not very hard to do, so give it a shot. All right. So imagine that you have a solution to the Laplace equation. So you've got the potential function and the stream function. And what we'd like to do is from that we can calculate the velocity. And then we can use the Bernoulli equation and insert this velocity that we have into the Bernoulli equation and then solve for the pressure, right? So this is the pressure, or this is the equation that relates pressure and velocity. A couple of things about this equation. I've written it without the hydrostatic pressure, right? Normally there's another term here, something like plus rho gz. And I didn't write the term here because we can really think of this term being embedded into the pressure term. So the hydrostatic pressure together with the thermodynamic pressure is an easier way to write these equations. I wrote it here. This is the magnitude of the vector v, and or you could write it as its components, the scalar components u squared plus v squared. That's really the scalar sum, right? It's u squared plus v squared, quantity squared, the square root, and then that quantity squared, so the square and the square root cancel to leave just what I've written there. Another thing is this is valid along a streamline, right? And so I picked some location along the streamline, far, far upstream. That's the infinity location. So you can think of this as far away, either upstream or downstream, far away from the action, basically. So we should know the pressure and we should know the velocity far away. It's essentially a boundary condition that we use to solve for that Bernoulli constant. So we should know this term and this term a priori, and then we'll get this from the Laplace equation, and then we can use Bernoulli to solve for the pressure. So that's really what we're up to here. Let's think about, for a second, to recall the Bernoulli equation assumptions. Basically, as I mentioned, I'm including the pressure, the hydrostatic pressure within the total pressure, so I've written this as big P. This equation is steady, as it's written here. There is no partial T term. It's incompressible. And really, that is implicit in the assumption that the stream function exists. Remember, the stream function is defined as solving del dot V, which is the incompressible continuity equation. So by default, if we're going to use psi in our derivation, if we're going to talk about the stream function as existing, then it is implied that the flow must be incompressible. That doesn't have to be the case, but that's the case here when we're using the Bernoulli equation. Let's see here. It's inviscid. I mentioned earlier that the existence of the potential function is related to the shear stress, and we set that shear stress equal to 0 in irrotational flow, and if all of the cross terms R0, then the shear must also be 0. So that results in no shear stress. And the other way we can get at that is to say, well, the viscosity is 0. So either way, we end up with an inviscid flow. There's no heat transfer, it's adiabatic, and it's reversible. And really, reversible and inviscid are kind of related in this sense, because without shear stress, without that irreversibility, then the flow is reversible. All right, so all of that said, we have our definition of the stream function and the potential function in relation to what the velocity vector is. So it's no trick to take this function and break out its component parts and see that really this is just del operating on psi will give us this v squared plus psi squared with our square here. So moving forward from that, let's talk about unsteady flow for a second. This is our conservation of mass and our conservation of momentum equations. And if we made some assumptions that are relevant to the discussion here for irreversible flow, if we essentially say that the flow is irreversible, we lose this viscous shear stress term. If we also say that the flow is incompressible, then we lose this partial rho partial t term. So it's steady in time. Then we are left with this conservation of mass del dot v. I've divided out the rho here, and since it's we're assuming that it's incompressible, so it's constant, so I can pull it out of the operator del dot, and then I can divide through because rho is not 0, and so I'm left with just del dot v. And then the momentum equation is left here where I've combined this rho in with little p to make big P, and I've just got the advection or convective term and this unsteady velocity term here. So I can then use a little bit of trig identity to reduce this down to this equation here, which looks a lot like an unsteady Bernoulli equation. So I've got this 1/2 del phi squared, which is our kinetic energy term, and then I've got this plus p over rho, which is our internal energy term, and then I've got a time rate of change of phi, and so that should be equal to a constant. And it's no small feat to go from this equation to that equation, and I think I'll leave it to you to try your hand at this. You can find the solution to this in various textbooks and whatnot, but it is interesting to have at that yourself. I would give this a 3-bean difficulty, meaning if this is a coffee break, you're going to need some coffee to do this. It's I'll give you a hint, and that is there is a lot of vector identity. So the trick to doing this is you have to crack this convective term open using some vector identities, and I've given one here that yields the term that remains, and then it's left up to you to get rid of this term. And the way that you're going to go about that is to utilize that del dot v is equal to 0. And so there's some trig identities to relate those two together, and then that will result in your unsteady Bernoulli equation. All right. So now that we have a governing equation, we have the Laplace equations, and we have a way to convert the velocity field that we get to a pressure field, and we could also do this in an unsteady situation. What we really need now is a boundary condition. So the first one we're going to talk about is no flow through a solid surface. So think about a solid surface. I'm presenting one here, dy dz. This is in a rectangular Cartesian coordinate system. It's right-handed, so x points in the to the right here. That's right-handed, right? Yeah, that's right-handed. Okay, so x points to the right, and so I'm identifying this surface, the geometry, with the unit normal. The normal surface, the normal vector that describes this surface is n hat, and it's in the I direction. So this is this blue arrow here. And then there's some arbitrary velocity field that's fluxing through this surface. So what we want to do is we want to find what's the component of the velocity extending from this surface, what component of the velocity actually passes through this window, and then set that normal component of the velocity equal to 0. That would enforce no flow through a solid surface. So how do we get that normal velocity? Well, it's the definition of a dot product, basically. So v dot, the vector dot this unit normal, will give us the components of velocity that flux through the surface, and this is quite easy because this surface is aligned to the x-axis. It's just the scalar value v sub x. So in an Eulerian reference frame, we're not necessarily confining ourselves to this surface is stationary to that Eulerian reference frame. It could be moving. So if this surface is moving, we have an additional dot product. We would take our velocity vector and dot it with the unit normal, and then we'd have to set it to the plate's velocity dotted also with that unit normal. In most cases, we're going to assume that our boundary conditions are stationary, and if that's the case, the plate is 0. So our boundary condition simplifies. It's just v dot n is equal to 0, or in terms of the stream function and potential function, that's just the gradient with of the potential function with respect to whatever that normal direction is. In this case, that would have been x, right? So it would have been partial phi partial x, and then that would be the u velocity when we would set that equal to 0. In order to get the u velocity from the stream function, that's actually, remember, that would be the vector direction aligned to the plate, aligned with the plate, parallel to the plate. So that would be partial psi partial s. That would give us the u component of that velocity, and we would set that equal to 0. So those are the boundary conditions for phi and psi for no flow through a solid surface. Related to this boundary condition is the fact that we could specify the flow tangent to the surface, right? So remember, this is inviscid flow. There is no slip boundary condition. If we think of a streamline as the solid surface, there is flow along that solid surface, right? So we could want to specify what the velocity is along some surface as part of our flow solution. And so it's really easy enough to do. It's just the corollary to what we just did. Think about the streamline that I have here illustrated in blue. The velocity along that streamline is everywhere tangent to the streamline. It's made up of its components, u and v. So here's our vector again with the scalar components, u and v and w. And it also has a position vector, that's partial x partial, or dx dy. And if we want to specify what the velocity is, we just simply take the definitions of the velocity. So that's the derivative of psi with respect to y is u, and psi with respect to x is minus v, and we just insert our boundary condition there. So we just pop those guys in there from our boundary condition, and from the Cauchy-Riemann equations we can do that with the potential function as well. So that's also in a way utilizing this no flow through a surface, but tangent to the surface, right? Okay, so that's one boundary condition, or two. It's one idea with two boundary conditions. Remember, we need 2 per unit direction, so that's 2 there. Another one is to think about what happens at infinity. So typically what's going on in a problem is we've got maybe flow around a sphere, and far, far away from the sphere, we would like to recover the free stream boundary condition, the flow, the undisturbed flow. So the idea here is that we calculate what the velocity is, or the pressure is far, far away. We utilize that as a boundary condition. So again, we would take this derivative and evaluate this derivative as x and y goes to 0. And in the case of a parallel uniform flow, like flow in a wind tunnel with a sphere and the flow is flowing over it far, far away, the flow would just be the normal parallel, horizontal, free stream, constant velocity. And so that would be u infinity, and no velocity in the v or y direction, so that would be 0. And likewise, in psi, we can specify the same conditions. It might be that the flow far, far away is 0. Maybe for the case of something rotating very near zero, like a vortex, that we want to then confine to that area, then it might be that the flow far away is zero. So we could allow V infinity to be zero, and we would call that boundary condition a quiescent boundary condition, a still flow in which we do something to it, like emit a source or something. And it's also true, not necessarily true, that this is always going to be zero, right? It could be that the flow far away has both x and y components, so it's customizable. All right, so those are our two boundary conditions that we need to satisfy the second order nature of the Laplace equation. So I thought I would do an example where I solve the Laplace equation using separation of variables to get a kind of a baseline solution, just to see how it all goes together. So as I said, we're going to use separation of variables, and that means we're going to assume that this potential function can be represented by two functions, f of x and g of y. So f takes on all the functionality of x, and g takes on all the functionality of y. We're going to seek a solution over some domain. So we're in Cartesian coordinates, so I'm in an xy domain here. And I'm going to look at just some plane, and I'm going to seek a solution for what's the flow inside this plane. The plane is bound by x equals 0 and x equals L, and y equals 0 and y equals h. And I have to specify boundary conditions. That's the way differential equations work. You know, I think of differential equations as like a musical instrument, right? The Laplace equation itself is the musical instrument, and it can play any song you want, but it doesn't play that song until you hit the notes, until you constrain that instrument in some way. And that's what boundary conditions are. They're the constraint that give you different outputs, right? Different solutions. Or in the case of a musical instrument, a different song, right? So the differential equation is a general equation, and it doesn't become a particular equation, and we don't get a particular solution without boundary conditions. All right. So the boundary conditions that we're going to specify are that the x direction of velocity everywhere on the boundary is constant, and it's this big U sub x, and then everywhere on the boundary the y direction velocity is 0. So really this is a horizontal flow, right? We're imposing just that we have a constant flow field across the domain. So it's a very simple problem, but it illustrates all of the key features. Now, if we're going to do separation of variables, I've specified the boundary conditions in kind of the scalar components u and x, but what we really need is them in terms of the potential function, and more specifically, we need them in terms of f and g. So we have to transform the boundary conditions from u and v to phi. And so how we do that is we take the derivatives of phi using the definitions of how we connect them to the scalar variables u and v. And then we recognize that if I take the derivative of this with respect to x, right, then what would I get? I would just get the derivative of f of x with respect to f with respect to x. And so I would get just this component, and then I evaluate it at x equals 0 and x equals L, and set it equal to the boundary condition u of x. And likewise, when I take the derivative of phi with respect to y, I'm really asking for g to perform that, to satisfy those boundary conditions. So it's the derivative of g with respect to y, evaluated at y is equal to 0 and y is equal to L, it should be equal to 0. All right, so I have two boundary conditions in f, two boundary conditions in g, and I'm ready to go here. So I'll start by inserting the definition of the separation of variables into the Laplace equation. And so I'll perform that operation, and you can see that by some rearrangement, I end up with this equation right here. So I end up with just that it's partial squared f partial x squared plus 1 over g partial squared g partial y squared is equal to 0. And this right here is separation of variables. If you notice, this first term here is only a function of x. This second term is only a function of y. But when I add these two together, the sum is always equal to 0. So how can it be that x and y are independent variables? So I can vary x all I want, and y can't vary. Or I can vary y all I want, and x doesn't have to vary. These two functions, or these two variables, are independent of each other. So how can it be that both of these can do whatever they want, yet the sum of these two terms is always 0? Well, the only way that can happen is if each individual term, if this and this are both equal to a constant such that they sum together to 0. And so that's the crux of separation of variables, right? So this allows us then to take this original partial differential equation and separate it into two separable ordinary differential equations. So each term then has to be equal to minus lambda. So this gives me that 1 over f partial f squared partial x squared is equal to minus lambda, and the g, or the y functionality, is equal to plus lambda. So that you can see they would sum together. And I've successfully separated this equation into its two parts. So we can solve this first equation. It's quite easy to solve. If I rearrange it, you can see it's just f double prime, where the prime here represents a single derivative, f double prime minus lambda f equals to 0. This is pretty easy to recognize. This is would represent a kind of a mass, and this would represent a linear spring. So it's a mass spring, so I'm expecting some oscillatory behavior in the solution, right? There is no damper here, so it would just oscillate forever. So the general solution to this problem is the combination of the exponent of the exp of the square root of lambda times x plus exp minus square root of lambda times x. And we know that within this trig function is sines and cosines, this oscillatory behavior. That's great. That is the general solution. However, for the boundary conditions we have, you can't satisfy this equation. That's pretty interesting. And so I think I'll leave it to you to try this out yourself. It's not very hard to see that if you plug in these boundary conditions into this general equation, you will not be able to calculate what C1 and C2 are. I mean, that is the objective, right? So that's true for an arbitrary lambda. But I can satisfy these boundary conditions if I let lambda be equal to 0. So in the special case where lambda is equal to 0, I can get a general solution. I can't find a particular solution for this given set of boundary conditions. So first off, if I set lambda equal to 0 and I resolve this, it's no trick to see that if I get rid of this term, that the second derivative would yield that the function f of x is equal to some constant x plus some times some constant x, c1 times x plus c2. So I have two constants here. So I can apply the boundary conditions. If I apply the first boundary condition, that I take the derivative of f, then I'm left with just c1, and I set that equal to the free stream velocity u of x, then you can see that I'll get that c1 has got to equal u of x. And to apply the second boundary condition, I got to take the derivative and set it equal to u. That should be u of x. Yields that c2 is arbitrary, right? That's kind of interesting. So I didn't satisfy, or I didn't necessarily utilize both of these boundary conditions to satisfy c1 and c2. I'm left with that c2 is actually arbitrary. And that's actually true. We'll see later when we begin to use this solution. This is the solution for a free stream inlet velocity, that the values of the stream function are in fact arbitrary. So we'll just put that on hold until the next lecture. All right, let's carry this out for g of y. Oh, no typo here. This is g of y here. So the general solution if lambda is equal to 0 is that g of y is equal to some constant c3 times y plus c4. Again, I apply the boundary condition that at the edges the velocity in the y direction is 0. That yields that c3 is equal to 0, and again c4 is arbitrary. So together, the two boundary conditions yield that the particular solution in terms of y is just a constant c4. All right, so I reconstruct the solution from separation of variables by multiplying f of x and g of y together, and I get this linear function here. And I should note that, or you should notice that we can do one simplification, and that is that c4 has got to be equal to 1. Because if I apply the boundary condition to phi, the potential function, the boundary conditions were that x is equal to 0 and at the location of L, that should be maybe h or just arbitrary y, the velocity is u of x. So by definition, the gradient of psi with respect to x is equal to u. So the gradient of my particular solution is here. I'm left with c4ux. So that would mean that c4 has got to be equal to 1 in order for these two to be the same. So that's a little bit of a simplification. So we have one arbitrary constant, basically c2. So the solution in terms of phi is that the flow is linear with respect to x, and there's a constant of integration. I can use the Cauchy-Riemann equations to cast this in terms of the potential function, to cast it in terms of the stream function, and I will leave it to you to do this. It's quite easy. So I would give that a one bean sort of difficulty with a helpful tip there. All right. Let's see. Did I leave anything out? We'll use this baseline solution. This is the uniform flow solution, as I mentioned earlier, and this is one of what I'm going to call the building block solutions that we're going to talk about in the next several lectures, where we build up to more complicated solutions. And keep in mind that although this is a simple linear solution, I can add to this simple linear solution more and more complex solutions to build up very complex flows. All right, so to wrap things up here, we derived and characterized the Laplace equation. We discussed how we obtain pressure from the Bernoulli equation. We discussed unsteady irrotational flow. And I introduced the boundary conditions, and I ran through a quick example using separation of variables as to how to get a general solution for the Laplace equation. All right, next time we're going to go forward. We just derived the uniform flow. I'm going to do it again in the next lecture, and then we're going to talk about sources and sinks and vortices. So from here, I guess we are done, and I will see you next time.